Hi everyone, we're CSE 3 and our project is Deep Learning Models for Reconstructing Sparse Ocean Dynamics. I'm Sahana.
I'm Advika.
And I'm Chloe.
So first we're going to go over our background, then the current challenges, then the goal, then our materials and methods, then the results, and the future plans and conclusion. So first of all, to introduce our project, next what is ocean dynamics? So, ocean dynamics is an extremely important field of study, and it helps us with predicting climate patterns, weather extremes, and long-term environmental challenges. Sea surface height is an aspect of ocean data, and it's critical because it reflects changes in sea level, ocean circulation patterns, and climate-driven events like eddy shedding and rogue waves. So, what was the challenge that we worked on these past few weeks? Um, so the challenge we worked on was reconstructing missing data, and missing data leads to an incomplete ocean understanding of ocean dynamics. It also limits predictive modeling and response to climate events. So sparse ocean data is often noisy and incomplete, like you can see in picture B. And this is because of limited satellite coverage, sensor limitations, and physical constraints like cost, geography, and weather. So sensors are what capture the data, and they have low spatial coverage. They operate in a 3D domain with noisy and nonlinear dynamics, and they're often deployed in remote and low connectivity areas. They also require edge computing. So this is an example of good ocean data versus sparse ocean data. The sparse ocean data is the image you see to the left, and you can see how there's not much data. It's very hard to see and it's hard to make predictions off this. So traditional methods of reconstructing sparse ocean data come from physics-based systems. However, they're computationally expensive. You need prior models. They're difficult to incorporate real-time sensor measurements, and you often need dense data and problem specifics. However, deep learning models are an alternate solution which work much better because they're computationally efficient, they don't need prior models, they leverage patterns in data, and they are able to reconstruct missing data, handle noise, and adapt to irregular outputs. So before conducting our experiments, we looked at what other people were doing to solve the problem of reconstructing sparse data without using traditional physics-based methods. Three solutions we came across were GenDA, Sensever, and RecFNO. And through these, researchers were able to preserve fine scale structures, which are critical for climate and eddy studies. Uh, their outcomes outperformed regression and physics-based methods in accuracy, resolution, and generalization. And they were able to scale across resolutions and densities, different sensor densities for real-world applications.
So the goal of our project was to use two models, the unit and the CNN, to reconstruct a sparse variable. And we chose this to be the sea surface height over the Gulf of Mexico because it had something called loop currents that we wanted to study, and also because it had easily accessible data. So to do this, we used neural networks, and these are models that are really good at identifying patterns in data. So that could be image classification or approximating different functions. And how it works is that data is passed through the input layer, and then it goes through the hidden layers, which perform a lot of calculations. And these calculations are different weighted sums. And as the model is trained, the weights get adjusted, and so the model is able to capture all the different patterns in the data. And the specific neural network that we used is the CNN, or the convolutional neural network. And this is particularly good at processing images and spatial data. So for example, detecting objects and segmenting images. How it works is that there are these convolutional layers which consist of convolutions and pooling. Convolutions are matrix operations that are applied onto the data, and they work as filters or kernels and capture the patterns. So they start off with capturing more simplistic features, for example, edges, and as the layers build up, they learn to detect more complex features, for example, shapes and even objects. And in convolutional layers, they also have pooling, which downsamples the data and kind of sees the bigger picture and the crucial information. And after the features are extracted from the convolutional layers, the data goes through the dense and fully connected layers, which classify the data and combine all the different learned features. And the specific CNN that we used was the UNet model, which is really good at segmenting images and reconstructing them. So shown on the left is image segmentation. It figures out what is in the image and where exactly it is. So for example, the cars are labeled with a dark blue color. And with image reconstruction, sparse and noisy data is passed in and then it is reconstructed. How it works is that the data is passed through the contracting path, which is which determines what exactly is in the image. So it has these different blocks, and each time it reduces the resolution to focus on a bigger picture and capture the global context. And after it determines what exactly is in the image, it goes through the expanding path, which restores the image to its original resolution to the high resolution. And it does this by each time it upsamples the data, it looks at the block below it to see what exactly is in the image, and then it uses a skip connection to go to the corresponding block on the contracting path to see where exactly the pixels should be labeled. And after this, it creates a really high quality image that does what the unit is supposed to. And the data set we used for this was this science-based ocean data set coming from the Copernicus Marine Service. And the variable that we focused on was the sea surface height, which in our data set was called the ZOS, but we'll be referring to it as SSH in our slides. And the shape of our data set was the number of days, which was 3 years or 1,095 days, the number of channels, which will be shown on the next slide, and the latitudes and longitudes over the Gulf of Mexico. So these were the two channels in our data, the sea surface height, ground truth, and the land ocean mask. Where the sea surface height is higher, it's a more yellowish color. And for the land ocean mask, where it is land, it is purple and 0, and where it is ocean, it's yellow and 1.
So the next thing that we did was data preprocessing. And the first thing that we had to do was normalize our data. We normalized our data by using programming to proportionally rescale our values to the 0 to 1 range. This makes our data more consistent and easier to analyze, and also prevents features with larger values from disproportionately influencing the model. Next, we each created sparse data sets to train our models on. We each were assigned a sparsity value. For example, I did 30%, Chloe did 60%, and Sahana did 90%. And we mainly created our sparse data sets by using programming to randomly select either 30, 60, or 90% of our data and set that value to 0, creating the sparse and noisy data sets that you see on the screen. Here is a larger images of our sparse data sets next to the ground truth of the SSH values. And as you can see, as the sparsity values increases, it's harder to analyze, which is exactly why we need to use deep learning models and machine learning to reconstruct the sparse data to make it easier for scientists and um, other people to analyze and understand. So just like we showed in the beginning of the slideshow, we also created an animation of the SSH values across 100 days. On the left side, you can see the ground truth of the SSH, and you can see how this changes over the course of 100 days. On the right side, you can see the sparse values, and you can see that at each panel, it's a different sparsity values are shown. And this is because at each panel, we chose different randomly selected values, which is exactly why it makes our data so random, inconsistent, and also, again, emphasizes the need to um, reconstruct this data. So just like Chloe mentioned earlier, the first model that we used was the CNN. And overall, just looking at the images, you can see that while the shape the CNN model predicted was pretty accurate, the color is very off. You can see that the CNN model predicted the color to be closer to the zero point 0.8 value, when in actuality, it's supposed to be closer to 0.6. Um, Overall, each of us trained our model around 100 to 120 epochs, which took around 12 to 15 hours. The next model that we trained was this unit model, and just by looking at the pictures, you can see it's a lot more accurate than the CNN. The shape, both the shape and the color are very similar to the actual SSH values. Just like the CNN, we also trained it on 120 to 150 epochs, which took around 15 to 20 hours as well. So besides analyzing the images, we use two main evaluation metrics to show our performance of both the models. So the first one that we tried was the root mean square error, or the RMSE, which measures the deviation between the prediction and the truth. As you can see on the equation here, the RMSE is basically the squared difference between the prediction and the truth, the sum of all the values in the data divided by the total number of values and the square root of that. Because of the square difference, it makes this evaluation metric very sensitive to large errors, which is also what makes it such an effective metric. The second evaluation metric we use was the fast Fourier transform, or FFT spectrum. This evaluates the frequency preservation and measures how well our model reconstructs both high and low frequency ocean dynamics. Here's a table of our RMSE metrics across all three sparsity values and the UNet and CNN model. As you can see, just by looking at the table, you can see the UNet performed a lot better than the CNN, as the UNet performance for the 30% sparsity was 0.006557, which is extremely accurate. Another thing we noticed was as the sparsity values increase, the error actually increases as well. And this makes sense because as the sparsity increases, the harder it is to 100% predict the sparsity values. So the second metric that we used was the FFT spectrum, and here's our example for the CNN model used for 60% sparsity. As you can see, both the lines for um, both the original and the predicted spectrum are very similar in shape. However, if it was 100% accurate, which is hard to achieve, the lines would be completely overlapping on top of each other. But in this case, you can see that there's a little difference, showing how it is not completely accurate and there's room to improve in the future. Due to time constraints, we were only able to create the F50 spectrum for the CNN for the 60% sparsity, but in the future, we hope to do this for the rest of our models and sparsity values as well. Overall, from this research, we learned that deep learning models such as the CNN and UNet models can successfully reconstruct sparse oceanic data. And from these two, the UNet performs a lot better with an increased accuracy and lower loss. This is also due to its encoder-decoder architecture and skip connections. We use the RMSE and FFT spectrum to help us visualize the accuracy and performance, and we're able to also analyze the difference between the 30, 60, and 90% sparsities. Overall, we learned that machine learning is a very promising and effective alternative to the physics-based models. In the future, we hope to try other models like the Fourier neural operator, or FNO, denoising diffusion probabilistic models, or DDPMs, and attention-based models. We also hope to explore other variables such as ocean zonal velocity, meridional velocity, and expand beyond the Gulf of Mexico. Some limitations that we faced in this project was being constrained in our dataset size, because while our dataset was over 1,000 days or 3 years, we couldn't go further than this because of limited memory and GPU, and we also didn't have access to retro computers. In the future, if we were to have access to these high technology resources, then we would increase the size of our dataset to make it more generalizable across a lot of different aspects. As part of this research, each of us wrote our own paper based on reconstructing sea surface height over the Gulf of Mexico using deep learning models, and we hope to work together to publish this paper in the near future as well. These are the references we used, and we'd like to thank our mentor, Nilufar, for all of her support and guidance. This research truly couldn't have been possible without her. We also like to thank UC Santa Cruz and the SIP program for this amazing opportunity. Thank you.